Okay, so we were right here. We were working, we had done the taxi cab. We got stuck a little bit right in this part, so let's hit this. For standard deviation, because that's just the spread, how much things move away and together, then you don't use this constant number. Because remember, it doesn't matter when you add and subtract, just when you divide. So once you set up this formula, just cross out the 250, that doesn't matter. And then I'll take my 1020, divide it by 2, and I will have 5.1 miles. So the only thing we had left was our density curve. The first thing is, what is a density curve? A density curve has two characteristics. One, everything is above the x-axis, so the entire curve is above the x-axis. That's one. And two, every time we say entire, that means that the area under the curve totals 100%. So you can't have some of it above and some of it below. So you could have, let me give you some examples. A curve like this, all of it above the x-axis. A curve like this, all of it above the x-axis. A curve like this, all of it above the x-axis. Symmetric, skewed right, bimodal. When would you use a density curve? If you're trying to look and find the median versus the mean. Because then you can see, how does this number compare to this number? And it changes depending on what the curve looks like. How can you identify the median? Okay, so you say to yourself, well, I know that median is the middle. So the way I identify where the median is, I just need 50% of the data on the left and 50% of the data on the right. So if the data is symmetric, then it's easy to figure out where the median is, because visually that's easier to split. If the data is skewed to the right, it's a little harder to figure out where 50% of the data might be. Okay. So in our book, it shows us where could we cut it, and you can kind of visually guess where can you cut it so that there's half the data on this side and half the data on that side. Then on the last page, how can you identify the mean? Okay, well, the mean is not in the middle. Remember, the mean is sensitive. So one big value can really pull it up. So if it is symmetric, then the median is in the middle and the mean is in the middle. They're together. But if the data is skewed to the right, then the mean is somewhere getting pulled up here. So the mean is further up than the median. Now in our book somewhere, it shows you some pretty good pictures of this. You can't see you can't see my book, so you're going to have to open to your book. I'm going to tell you what page. Try like page 100 and, can you hear my book flipping? 102. Okay, on page 102, it says, if this is the median, where would the mean be? And the mean works like the balancing point. So the balancing point is, where could I put a little line, a little like maybe rock underneath? Pretend this were like a seesaw. Where could I put a rock underneath and this thing would balance? So the mean is where I could have a little rock. I'm on page 102. Or a little fulcrum for you science people. And it wouldn't tip to this side and it wouldn't tip to this side. It would just balance out. Okay, so that's how you do the mean. The median, 50% of the data, would probably be about right here. So does that look like 50% on that side, 50% on that side? So the green one is the median. The red one is the mean. The green one is so that there's 50% on this side and 50% on this side. The red one is so that it will balance. And I got all that off of page 102. And then for the end of these notes, you only have to do the 3 and 4 on check your understanding. So it's going to ask you to trace a curve onto your paper and then mark the mean and the median. So you'll probably need page 102. That's what we were supposed to finish yesterday. So now get out your new set of notes. If you have this movie, you have these notes because I would have given them both to you when you came in. So now we're looking at our 2-2. You're going to need your calculator. We're going to look at something they call normal distributions. And the first thing says, what is a normal distribution? So let's look at one. In 2009, the distribution of batting averages for Major League Baseball players was approximately normal. See how they use a capital N? That means this is some ideal. With a mean of 0.261 and a standard deviation, you should get in the habit of circling things. Sketch this distribution, labeling the mean and the points that are 1, 2, and 3 standard deviations from the mean. Okay, let's talk about what a normal curve is. A normal curve is a density curve. So it's all above the x-axis. 100% of the data fits below. The mean fits in the middle. So what did they tell me the mean was? 0.261. With a standard deviation of 0.034. So this is the average distance that spreads out. On a normal curve, you go 3 up and 3 down. Do you see those little marks that were on the paper? So if the middle is 0.261, then this notch is 0.261 plus 0.034. I'll write that in, 261 plus 0.034. And then this one is 261 plus 2 standard deviations plus another. So you need your calculator. 0.261 plus 0.034. 0.295. Okay. Then you add another 0.034. 0.329. Then you add another 0.363. Okay, question. How do you think you get the numbers down here? Just add and subtract the standard deviations. So if I want to get the number down here, I'm going to have to go 261 minus. So 0.261 is the middle, minus 0.034. So now I get 227. And you can go from there. You can find this one and this one. Okay, now it says, explain what the points at which the change of curvature take place. For those of you who are in higher math, you've heard the word maybe points of inflection. Okay, so a point of inflection is this. It is when, okay, look at this curve. The book says, imagine that you're skiing, you're right up here, standing up here, and you're going to ski down the hill. A point of inflection is as soon as it stops from going down really fast to starting to slow down. Because if you don't start to slow down, oh, it's going to be bad at the bottom. So the point of inflection is about right here, about right when it starts to slow down.